Hi, I'm Chris Williams. I'm a Tata Steel employee, those of you who don't know me, but I'm seconded and have been to Industry Wales, which is an arm's length Welsh Government body. It's there to give unfettered advice to Welsh Government ministers on industry matters. I was seconded there because as Tata in Port Talbot we were exploring our decarbonisation options probably 10 years ago, trying to understand what the future looked like, understanding what was happening in Europe in particular and rest of the world, but starting to develop the understanding that we were going to need CCS or CCUS, CCU and CCS, and hydrogen and electrification going forward. So we needed to be in a region that was developing the infrastructure that we knew we were going to need depending on what option we were going to choose going forward. We weren't. There was a lot of academic work underway, but the region, and there's no real control over the region in terms of understanding and developing the infrastructure. So we started up working with the other areas of the UK. So we worked with Humber, Teesside, the North West and Scotland on understanding what industrial regions were doing, and lobbied government to support our industrial regions, what became known as industrial clusters, support them with infrastructure developments going forward. So I learned a lot off Teesside, I learned a lot off Humberside and the North West, and we were able to take a lot of learnings from those regions and bring them back to South Wales in terms of understanding electrification, in terms of understanding hydrogen, in terms of understanding CCU and CCS. So I'll make sure I keep them separate. So we set up the South Wales Industrial Cluster in 2019, and we won industrial funding. So we're now one of the main industrial clusters alongside Teesside, Humber, Scotland, North West, Solent, the Black Country around Birmingham as well came on board, and now there are other industrial regions. It's all around developing the industrial infrastructure needed to support their industries decarbonised. But I'm here to talk about thermal energy, and why I talk a little bit about that as an introduction. Of course, as our industries look to decarbonise, as they maybe look to move away from natural gas to hydrogen or electrification or a biofuel, or they look to use CCU or they look to use CCS, thermal efficiency is key and core to all of that. All of our industries will need to make sure that they are as efficient as they can be in their final derived net zero solution. And I've only on one bullet now, point 1 of 13, so I'll try and go through this, but I thought I'd take you through a bit of my history. I graduated in 1990, was a frontline engineer then until 2008. Hadn't had anything to do really with academia. I'd supported students, etc., but not properly. In 2008, I was called into the office by the technical director and said, "Chris, we volunteered you to do a part-time PhD." I was like, no. But I went through it, and in effect, I was given no choice. I was old. I was 40. I had 3 children, so I wasn't going to leave. So Tata had decided that I was an ideal applicant to do a part-time PhD. So I ended up picking waste heat recovery, so again fits in with thermal energy, and I did it on waste heat recovery. Because at that time I was based in the Boss plant with Matthew, as we were exploring our energy bridge. So as a works area, we had a bridge with our actual energy consumption, with a theoretical minimum energy consumption, but world's best practice. It was how do we bridge that gap between the two? So we were researching and exploring technologies. It's what we call the wave, energy wave, now within Tata. So waste heat was seen as an opportunity, but we struggled really to explore and have the capacity to explore options, which is where I think this story is a great example of academia and industry working together to develop the initial understanding and also to develop the business case. So with my PhD, we then started to model and explore different ways further forward, understanding the heat balance, the thermal efficiency of the Boss plant, and understanding the opportunities around the world. But also, if we collected waste heat, what would we do with it? Which is the question that we struggled with. And that's where academia really helped us. So working closely, we modelled lots and lots of different options. We decided on a route. We verified the model and verified our way forward. Ended up as adding £20 million to a planned business case, and it saved £8 million a year in electricity generation because we were using waste heat to generate electricity. So that was installed in 2013. So that to me is a clear example, and why I've always had a passion since then to make sure that academia and industry are working as closely together as possible, because I've seen practically the benefits. And as we saw from some of the posters earlier, there's clear work. They all start with ideas that build and grow and develop. And as long as industry we can stay engaged properly, we can support and develop through to implementation. So waste heat recovery was my PhD, and I think that's why I was asked then to be to chair this. Thermal efficiency as a whole as a topic, I think lots of people might think, okay, that's a well-trodden research area. It's old, there's not really any point in exploring that, but that's completely wrong. As industry now, as we're looking to fuel switch to hydrogen, as we're looking to electrify, as we're looking to use CCU, as we're looking to use CCS, there needs to be a whole new look at thermal efficiency. Almost the rule books need to be rewritten. We need to start on a whole new process of working with academia, mapping and developing and optimising our way forward. So thank you for the introduction to chair this session. When we look at electrification in terms of heat pumps, improving the thermal efficiency of heat pumps. When we look at induction heating, look at the thermal efficiency of induction heating, etc., etc., etc. And then when we come to the waste heat that the process will probably still emit, then how do we capture and what options have we got? And we'll hear again options from that. But of course then in terms of refractories, in terms of furnace linings, in terms of insulation on distributed heat networks, all of that is thermal efficiency, and all of that we need to start and draw a line and start again on a new research program supporting thermal efficiency. In fact, I was in a dinner in the Royal Society about 2 weeks ago. We're there debating starting a new Royal Society research program on industrial thermal efficiency, which was good to hear. So I think this is very relevant, very interesting from our perspective as industry. So I think that's enough of me talking as an overview, but I wanted just to go through that. So now on to the talks. I'll introduce you to Cameron. You're going first? Yeah. Cameron.
Thank you. I've got to keep an eye on the time.
Got a reputation.
Right. Okay, so this is that bit isn't fun, but this is the fun bit of Sustain for me, because it's something that I'm actually doing to contribute to some of the research outputs, as well as just trying to keep the whole thing going and all that sort of stuff. So, Becky pushed me for a title because, like many things, I was kind of the last person to provide one. And I was trying to think of something snappy, and I just said off the cuff, cooking on gas, because I don't like simple titles. And then I was like, oh my God, how am I going to justify this? And then I was eternally grateful to Ed to then come and tell everybody how 50% of his CO2 was based on NG. Yeah. So now I've got a good justification for the talk at least. And I want to talk about refractories as an oft overlooked but incredibly important material in steel making, and try to justify to you, one, why I think they're so important, two, why they're so interesting, and then three, some of the really interesting research challenges that we've got around that. And then I'll say four, why we can't solve all of our problems with refractories, which should hopefully lead on neatly to the work that's going to be presented by Helena and John in a minute. Tell them what you told them. Refractories, why are they so critical? Our approach to sustain, in sustain. And this is just, I have to say, this is just one element of what sprawled into a huge program as a function of aligned resources as well. So there was some work on thermoelectric generation. There was the work that Caden presented just now as well on how you actually get the heat into the material in a very efficient way. So we're not just looking at this in a narrow way, but there's a limited amount of time, and so there's only a few things that we can present out of this wider activity within sustain. And I'll go through a few case studies to demonstrate why they are so exciting and so important. Right. Refractories, are they critical? Well, if you're stood next to a ladle and it's full of liquid steel and there's 300 tons in there, they feel pretty critical to you at that instant moment in time. Yeah? They're essentially the interface between an extremely complicated, extremely high temperature process and the person, and so they have massive health and safety implications, they have huge energy cost implications, as was outlined by Chris, and they have massive CO2 implications, as was outlined by Ed. So luckily I don't have to repeat any of those things. And much as we would like to design our way out of this problem, you still have to heat steel, or iron in this case, up to 912 degrees if you want the phase to change, and you still have to heat it up to about 1538 if you want it to melt. Yeah? So these are probably unavoidable things that mean we're going to need to have some sort of sensible interface between ourselves and the process that allows us to manage that whole thing. So this is a picture by Patrick up there. Thank you very much. I stole one of his pictures. And this is actually, I think they're just blowing out, is that let me get this right now, is that purge plug? Is it?
Lancing up the well block.
Lancing out, there you go, lancing out the well block. I should just say it like that, like I know exactly what I'm talking about, but I rely on these guys all the time. And this is actually a thermal image of exactly the same process. Okay, so you can kind of see that they behave, they're in extremely challenging environments. There's an awful lot going on. And therefore they have to be both robust but also thermally efficient. They're interesting materials, so they're kind of composites really. Kind of analogous to soil, like if you dug up a whole load of soil with a load of stones in it, it would kind of be a bit like that. It's kind of a load of rocks stuck together with some sort of matrix in many cases, although there are what they call monolithic materials, which are basically ceramic bonded to ceramic. But a lot of the materials that we work with in the steel making process are what we call carbon bonded. We don't use soil and biomass. We tend to use phenolic resins and some form of solid carbon, normally graphite, but can also be small spheres of carbon or fibers even, as you're about to see. And that we do that because it makes them easier to manufacture, but we also do that because it helps us to tailor the thermal properties of the brick. Okay, so I'm going to show you lots of different images of refractory microstructures, which I'm sure you're absolutely dying to see. But to give you but they all look slightly different because they're captured in different ways, and that's part of the story of the research that we're developing in sustain. So this is a bit of rock, okay, and then these white bits in this image. The very white bits are the resin, the binder, and then the slightly less white bits, the grey bits in between, are actually all of the carbon and the graphite that sits inside the material. And that's quite interesting on its own, right? Because it aligns in different directions. So depending on how you've pressed the brick, you can align the graphite in different directions. And if you look at learnings we have from other composite structures, so this is graphite in copper wires, so this is from electrical perspective, you can see that the orientation of the graphite has a massive impact on the conductivity of the material. And we did some interesting work where we looked at how we might be able to determine that relatively rapidly using simple characterization methods. So this is actually just an optical micrograph. It doesn't look like one because we've used only polarized light, so only light that's incident in one direction, and it happens to interact with the graphite in a way that tells you what the crystal orientation is. So if you look at this through a whole series of different rotations of that single plane of light, you can see that you get different colors. And you can actually translate this into what's called a reference sphere that looks something like this, which actually measures how elliptical or otherwise, how skewed the light is or otherwise when it gets back to the detector. And then you can plumb all of that information into a calculation, which then actually tells you what the orientation of the graphite is. And so you can sort of put that against the reference sphere up here. And so there are things that are important for us to clarify and characterize in refractories that have a massive impact on the thermal efficiency of those materials. So this carbon is an important part of the context for our research. The other thing about carbon is that it tends to either pyrolyze or oxidize in the presence of atmospheres. So if you're burning natural gas in a furnace, or you're preheating a ladle, or you're something with the well block, lancing out the well block, obviously, then you will going to do some horrible things to that structure in terms of interacting between the environment at high temperature. And we have used a technique which I haven't explained yet, so this is a little bit backwards, to look at, non-destructively look at the material. So this is the rocks again, and I apologise, we've now flipped the colour chart, so this is the rocks, and then this is the carbon and the graphite around the sides here. And you can see that if you expose it to oxygen at high temperature, then you will get a certain level of porosity if you do nothing to it, and then more and more porosity as you do. So you damage the material essentially. Yeah? Now the carbon's in there for a very good reason, and that is that one of the main damage mechanisms of refractories is thermal shock. So they don't just have to be good at insulating from the perspective of temperature, they also have to be very resistant. And why is that? It's because one of the main reasons that you will actually stop a steel making process is because your refractory lining is knackered. Yeah? We spend an awful lot of money trying to ensure the continuity of the process, and it can have actually a significant impact on the bottom line of the business. And one of the main reasons that you will get wear is a process of thermal shock, where, because these are transient processes, we fill and then we empty a ladle, for example. Refractories can heat up and cool down relatively quickly, and that creates micro cracks in the surface, which are then exploited either through thermal shock or a combination of thermal shock and chemical degradation, as we're going to see later on when we talk about gases other than natural gas. And then that can lead to a reduction in the strength of the material and rapid degradation of the products. So we've got to balance that against the thermal, and the one way we do that is by putting more carbon in. So ironically, the more carbon that you put in, the worse the thermal efficiency, but the better the thermal shock resistance, so you get something that's more durable, but less thermally efficient. And so those two things have to trade off on one another if you look at them in an isolated fashion, which we're not going to do. Okay, so what have we done in our work? We've looked at a novel characterization pathway. So the core work funded in Sustain looked at developing a novel characterization pathway for these materials, where we looked at multimodal characterization. So we got low resolution imaging of large samples non-destructively using X-ray tomography. And then we've looked at high resolution X-ray tomography, where we can get a better idea of the structure of the materials. And then that is correlated with scanning electron microscopy work that is able to dig down into the material. I'm sort of explaining this in layman's terms, or FIBSEM for people who know what that is. And that can be correlated also with optical methods as well. And the idea is you pull all this information together to learn more than you would have done before. And we know now that this is popular because people are starting to beat us to it on the publication point of view, which is immensely frustrating, isn't it, Nick? Yes. Okay. So I want to provide a few examples. So this is a refractory structure that isn't actually strengthened by a combination of phenolic resin and graphite. It's actually phenolic resin and fibres. And we wanted to see, with a high level of industrial relevance, how the distribution of those fibres change through the structure. So one of the things that you can do to try and improve this trade-off that you have between thermal efficiency and strength is to look at different forms of carbon in the structure, which might strengthen it as much for lower carbon additions, and therefore for less of a thermal efficiency penalty. And we've basically probed the limitations of the technique. So these are non-destructive images. So these are slices made up from 3D tomography. And you can see here hints of individual fibres through the structure, and also large areas of fibres potentially all clumped together. But in terms of actually resolving the size, shape, form, length of those individual fibres, which we were actually tasked to do, we found that really, really difficult. So what Nick did in a very painstaking way, Nicola's over there, by the way, is correlated this to simple optical, well, not simple in terms of how we did it, but more conventional optical microscopy, okay? So what we did is we identified a region where we had non-uniform distribution of these fibres to see if we could pick out the detail of that region. And we took the 3D volume and then correlated it to a 2D plane, cut the material in half, and then actually imaged that surface and placed it back into the 3D volume so that we could correlate an optical description of the microstructure with an X-ray description of the microstructure. And that looks something like this. So that's the region from the large area. That's what it looks like here. And then these are the actual individual fibers that you can then see embedded into that. So that allowed us to know that what we were seeing was a collection of individual fibers all stuck together, and we could correlate that back, meaning that when we looked at the rest of the volume of the material, we had a more representative idea of what was going on in the structure. And that allowed us to optimize the formulation of that product such that you could distribute the fibers better, lower the amount of carbon that you're putting into the system, increase the thermal efficiency without reducing the degradation. Okay, so it's just one example of how we've used this characterization pathway. Another one is thermal shock, so looking at that other method, so less the effect of carbon and more the effect of thermal shock itself, and actually the interactions between the process of thermal shock and the degradation of the carbon binder. So these are submerged entry nozzles, and this is work we did between Matthew and Ibrahima Salah, who's no longer, when I say no longer with us, he's not dead, but he's no longer part of the group. And we were looking at the how we could optimize the preheating, of these sends. So before you put them in, you want to make sure that you, this is for casting, by the way, so the material flows through here into the tun dish. And you obviously don't want to put them in cold because they just break straight away, so they need to be preheated. But when you preheat them, you then start to initiate that oxidation process, which reduces how robust they can be and can lead to premature failure if you do it wrong, which was happening. And so we worked between the refractory manufacturer and Tata to try and look at how we would do this, but sneaked in some cool characterization along the way. So we actually took some of the materials that were being used from those trials and then put them into X-ray CT to look at how the porosity as a function of the damage to that matrix was developing over time, which we're able to chart here. And we complemented that X-ray CT data of the porosity with two other techniques that told us something about why that porosity was developing. So we used both Raman spectroscopy here, which tells us something about the structural differences in the phenolic resin and the pyrolysis of the phenolic resin and the oxidation of the graphite itself by monitoring the relative sizes of this peak here and this peak here. To tell us how that was progressing as a function of temperature and time. And we also did excitation, so basically ultrasonic testing of these as well, to look at where we got the maximum level of damping through the preheat cycle. And where you have the maximum level of damping, you've got the lowest level of damage or crack formation. So you're basically able to use that to monitor the crack formation inside the material. And that enabled us to try and to basically optimize the preheat time, understand why it was optimized as a function of the degradation of the actual components of the system, and correlate that to what we were seeing non-destructively through X-ray CT to make it a recommendation on what you can do on that, which has the potential to significantly improve the productivity of the process. Because if you lose a sen in the middle of a cast, Matthew would tell you that's a big problem. Okay, and the last one, so we're cooking on gas of some form, and we might be cooking on gas of another form in the future. So Ed referenced the potential move to hydrogen in 2032. Not bad. Probably 2032, isn't it, if they tell you 2031. And this is, of course, a hot, or actually cold, because this process is endothermic topic, of hydrogen reduction. And I didn't come up with, I can't say I unilaterally came up with this idea, because the reaction of refractories with hydrogen and thinking about that has been going on for a long time. But in my own head, I realized this was an important idea. I'll tell you a little story now if I've got time. I was sat in an event which is fairly non-technical with the banks. I was invited there by the Energy Transitions Commission to comment on how we might finance the green transition. And most of the archetypes involve some version of hydrogen DRI in them that we were assessing and trying to find out how we might get to final investment decision. And the number one thing which changed the business case was the duration that the asset would run for and the productivity. But what's interesting about that is despite the big investment in H2 green steel and the work of hybrid, we still don't actually have an idea about what the maximum campaign length of a hydrogen DRI vessel will be. And one of the major reasons we don't know that, aside from the availability of the hydrogen itself, is that we don't know how long the refractories are going to last. Yeah? And a paper by RHO Magnesita, written in part at least by one of my, my old students, said the main wear mechanism to consider are chemical attack by process gas. Ooh, haven't we seen that somewhere before? Mechanical stress at high temperature, abrasion and thermal shock. So it's basically the same thing, but for a different reason, right? And we basically, me and Nick are in the process of replicating this paper, albeit using our novel multimodal characterization technique to learn more of why it is that, or how it is in the structure, more to the point, that silica is being reduced to silicon oxide and water, degrading the performance of those refractories. So we're doing this in a slightly different way to the paper, because they basically looked at a kind of a straight before and after, but we've actually analysed the material before it goes in. We've analysed exactly the same material as it comes out, and then we're in the process of using computer software to actually correlate individual parts of the microstructure together before and after. So this is CT data before and after, and you can see that the surface porosity has significantly increased, and this is all very hot off the press as in last week. We can also, it doesn't come out very well on this screen actually, but we've also noticed that the silica on the surface of the sample is significantly reducing, or the location of that is significantly changing before and after the hydrogen treatments that we're putting together. And so we hope to be able to present in future a direct correlation between these before and after microstructures so that we can understand more about that technique. So in summary, refractories are complex but brilliant. Yeah? And really, really exciting. If anybody wants to work in refractories, come and speak to me. We've developed this novel characterization pathway, and we've looked at all of these case studies demonstrating that it has value. There's inherent compromises that sit here, which mean that we might have to have more heat leaving the process than we would like, but that's what Helena and John are going to talk about, because if they can solve that problem, it makes our life a lot easier. Thank you very much.
Good afternoon again, everyone. My name's Jonathon Elvins. I work for Swansea University, specific IKC, and again, what I'd like to do is talk to you, following on from the work that Helena's just talked about, is looking at mobile energy stored as heat, or harvesting of low-grade waste heat using heat storage materials. So we are slightly different in terms of the work that we've done from Helena, in terms of looking at different technologies, but the concept is the same. So just to give a brief introduction, first of all, UK emissions. So in total for the UK sector, there's about 468 megatons of CO2 equivalent. Heat actually accounts for about 37% of that. And then we can break that down further to look at cooking, the industrial, space heating and hot water. And it's the industrial part, obviously, that we're focused on. And that's around 65.5 megatons of CO2 equivalent. And what we're trying to do, obviously, as part of the entire program here, is reduce that or reuse it so we can actually create a more sustainable future whilst maintaining the manufacturing industry, whilst maintaining the rest of the industry as well. So what if we can capture that waste heat from industry, we can transport it down the road, maybe just from Port Talbot to Swansea, or it could be, in the case of the MESH programme that Helena mentioned, in terms of capturing from Port Talbot and transported to Birmingham, and then we can use it as low carbon domestic heating. We could also use it as process energy, so a lot of the industrial processes within the steel industry could do with a bit of a pre-feed, get my teeth in, and heating up the air going in straight away. Lots of different uses for it, and as Helena has successfully demonstrated, it is possible to actually capture that waste heat and use it in a really significant way. We're not the first people to be doing this. There's a lot of different organisations around the world, both academic and industrial, that are doing it, and certainly demonstrations in Germany have shown with the phase change materials that Helena has talked about that it is feasible to capture that waste heat energy from incineration processes and transport it up to about 50 kilometres away from the original generation source and use it while still being more carbon economic than the actual more carbon economic than the actual generation process of something like a gas or a liquid petroleum. So, what could the potential impact actually be? Well, for a typical house in the South Wales region, you're looking at around a heating demand of about 10 megawatt hours each year. Actually, 1 tonne of steel produces or is equivalent to around about 420 kilowatt hours of waste heat. So all we would need is 6 4-tonne coils from the steelworks locally to actually equate to the energy for one house. And if we start to look at the city we're in, Swansea, what actually does that mean? Well, there's about 110,000 houses in 2020 in Swansea. Hopefully with the new government coming in, that's going to start to increase again. But if we actually captured just 50% of the waste heat from the Port Talbot Steelworks, we could actually heat all the homes in Swansea each year. If we were looking at the low-grade waste heat, which is the stuff that Tata don't really capture at the moment due to it's either technically difficult or it's economically unfeasible, we could use the low-grade waste heat that we would capture and cover about a third of the homes in Swansea for that year. So there is significant amount of impact we could actually have doing this, and hopefully it should be relatively simple. He says hopefully on that. So the materials that we're looking at are thermochemical storage materials. So it's a slightly different technology to what you've just been introduced to. So I'll take you through that. So we are using a combination of a matrix material and some salt. The salt in this case is calcium chloride, and you can see a really bad schematic of that on the screen. So calcium chloride can exist in two states, either with a series of water molecules in it or in its anhydrous form, i.e. without any water molecules. So if we apply a hot air stream to that, perhaps a waste energy stream, we actually have the thermal interaction between the bonds. The bonds break and remove the moisture away in the airstream, and it's an endothermic reaction, so all the energy required to actually break those bonds is then stored chemically within the material. We can then encase that in an airtight box. In the case of our demonstration systems, this will be a hermetically sealed steel box or aluminium box or something like that. In our labs, it's more about Tupperware, but whichever way you do it is actually it's very simple to do and actually prevents any energy leakage from these materials. To recover that energy, all we need to then do is put a moist air stream through it. The moisture recombines with the salt. That's an exothermic reaction, so it gives out heat, and we can transport that heat from the point of generation through to where we would actually use it. As I say, whether that's space heating or a pre-feed on the process. So what do these materials look like? Well, we've got two sets of materials that we're currently evaluating. On the left-hand side, we have our Generation 1 materials, which are vermiculite and calcium chloride. And on the right-hand side, our newer materials, which are a combination of calcium chloride, alginate, and graphite. Two different materials. Why are we doing that? Well, our Generation 1 materials we know are operational. They work really well. And what we're trying to do then is improve the energy density and the thermodynamics around the system. So by modifying the matrix that we can have in there, we can actually increase our energy storage density from about 150 megajoules per cubic meter up to around about 490 megajoules per cubic meter. We can also improve the thermal conductivity, so that makes the process a lot better and a lot more efficient. We can actually capture more moisture, and if you think back to the demonstration I've just showed you, the moisture is the fuel for the system essentially, so that enables a greater efficiency as well, and we can actually get more salt into the materials as well. Vermiculite is an interesting material which will have a benefit going forward with these sorts of materials, but it can't hold a lot of salt onto the system. So as a research group, we've looked at these materials in two different ways, through the discharge process and through the charging process. I'm here really to talk about the charging process today, which is about industrial waste heat. But what I thought was I'd just demonstrate to you that actually we can get some heat out of these materials. So this is a graph which details in about 40 grams worth of material up to about 400 grams of material. The profile is pretty much the same. What you can see here is the thermal uplift as we apply moist air into the materials over a 3-hour time period. The input temperature is somewhere between 10 and 20 degrees centigrade on this, and then what we're getting out is between 20 and 30 degrees centigrade. Doesn't sound a lot, unfortunately, does it? But the bulk material temperature in these is actually 60 to 70 degrees centigrade. So with a bit of efficient process and design in the actual system itself, we can actually start to elevate that temperature up to the 50 and 60 degrees centigrade. And with the help of the SUSTAIN program, we've actually had a PhD student who has been generating hot water in the 50 to 60 degrees centigrade range, which is actually becoming useful in terms of space heating. So looking at the charge process, we analysed a lot of different processes for industry. Some are static processes where a steel coil in the batch annealing process, for example, would sit in a stack, or some are dynamic. So we've actually looked through all the materials and had to think about where we would actually utilise the static and where we'd use the dynamic sort of charging processes. We focused mainly on the dynamic processes, but we had to demonstrate to ourselves and to the users that we can charge these in a static process. And what you can see in this chart is the generation 2 material, so the alginate beads, and over a period between 30 and about 140 minutes we can actually return the material from soggy and sopping wet down to anhydrous, which is the dry material that we want, which is fully charged. This can again be seen in the dynamic process. So if you look at the reaction chamber we have here, this is a flow control flowing hot air through into the base of the system. We then have a material within the system and plenty of insulation around the side, which will be the ceramics and the refractories in there. And what you can see over a period of time is that as the temperature increases and the interactions occur between the chemistry and the hot air stream, the mass of the system drops down until it plateaus. When the mass is actually plateauing, that means that all the moisture has been removed and we have an equilibrium in the process. So after about an hour, in each of the cases, we're getting very close to actually removing all the moisture and charging the materials. Okay, we can do that in the lab. What about actually doing that in an industrial process? So I can testify to Chris's thesis. It's a cracking read, first of all, and about 8 years ago probably we started to have the first conversations about how we could actually use these materials within industry and how we can actually start the process of capturing some of this waste heat. So working off 2 programs originally, and then working with the SUSTAIN program further on, and Tata Steel, we've started to analyse a lot of industry locations. So 3 locations within Tata Steel: Shotton in North Wales, and then Trostra, which is just down the road that way in Clethley, and Port Talbot Steelworks, which you'd have either driven past or come past on the train. 3 sites, each producing different things, each with different thermal loads and waste heat processes coming through. We sat down with each of the energy teams at each of these sites, had a detailed discussion around what are the processes, what are the waste heat processes, what is feasible to be captured, what can't be changed. So just a few examples at Trostra. There's only really 2 or 3 of their processes which are worth considering for actually the capture of waste heat. So the furnace stack on Capel, for example, the CRM, and the tin anode cast house, which I'll talk about further in a little bit. The rest of the processes, whilst there is some available energy there, actually it's probably more economically unfeasible to do it, and probably waste more energy than it would do in actually capturing it. Port Talbot, extremely different. Processes from 50 degrees centigrade up to over 1100 degrees centigrade. Lots of different areas that we could actually look at. So my colleague Sahan Souli, who was working on this work, spent a lot of time with the energy team, Jordan Bowie, I should acknowledge his work in this. And they were able to break all the processes down into the different areas, evaluate the different energies, and then convert that into the exegeus, so the amount of useful energy that's there. And between Jordan and Sahan, they came through all the different processes and looked at what is captured at the moment, what would potentially be useful to be captured, and what couldn't be captured with sort of current technologies. And it's that poor capture area, but possible to capture with a higher percentage within the SIM, that is the useful area. So the 4% at the top, and the 100 degree to the 200 degree range, which is useful for us. So these temperatures are useful, and we can capture all of that energy, or about 90% of that energy. But with current technology in terms of the heat recovery units, it would either be unfeasible economically or technically. So that's the area we focused on. So I will touch on Port Talbot again in a minute, but first of all, I'll take you back to Llanelli. The anode cast house. So Llanelli Trostra is a tin plating plant. So if you've got a can of lager or cans of water that are there, probably that material has been processed through the Llanelli plant. And this process behind me is where they actually produce the ingots for the tin plating process. So you have a furnace on the left hand side, which contains the molten tin. And in this region around here, where the burners operate, it's about 560 degrees centigrade. You've then got a series of stacks coming off the top, which go out of the building and then are emitted to atmosphere. By the time the gas gets to this point, it's around about 220 degrees C. So you're losing instantly, in the space of about 10 meters there, around about 300 degrees centigrade, which is an absolute ton of energy to be using. What we wanted to do was actually stick a device in this area around here, towards the back end of the IDRIT project. Unfortunately, we weren't able to do that because that would have been changing the process, and Natural Resources Wales were not particularly happy with that. So what we decided to do instead was to create what we've called the physical twin, which is essentially the same ducting system with our unit on the top under a chimney cowl, and then we have an industrial sized hairdryer at the bottom, which can create the temperatures. And what we proved within this system, both internally and externally, you can see it inside the house, inside the shed at this point, is that likewise with the academic in situ tests, we can actually remove all of the moisture from the system. And with the 250 grams of SIM, we get to anhydrous rapidly within the space of about 150 minutes. And then if we increase that with the red line there, we can actually get again to anhydrous. As we increase the amount of SIM, or we increase the distance between the end of the tube and the capture cage, the time to actually capture the energy increases, but we do actually bring it back to anhydrous, so we can actually utilise the system and store it properly. So moving forward, through in our interactions with Sustain, we're put in contact with the hot mill at Port Talbot, and we have a lovely process there where we've got a cast slab going through into the reheat furnaces. And then this photo on the right hand side is actually the furnace oven top. So there's a series of stanchions above there, a series of I-beams, and then temperatures in this region around here can be from 60 degrees centigrade to around about 220 degrees centigrade. So essentially what we have is a lot of waste heat coming through the roof of the furnace, and what we're looking to do is actually find a way to capture that. So what we'll be doing over the next 15 weeks is building a new unit which will slot inside the I-beams and create a cage around this system. We'll then have a fan on that unit which will direct the waste heat coming out of that unit and straight through one of our sim chambers. And at that point we'll be able to demonstrate the effectiveness of the capturing. Those materials will then be transported across the road from Port Talbot Steelworks to our shed building, and will be distributed into one of our test cells to prove both the charge and the discharge element. So in summary, there's plenty of waste heat to be utilised, and we have ways of capturing it, whether it's within the phase change materials or within thermochemical materials, or even in a sensible fashion. The capturing of waste heat is feasible, and it can be done efficiently and at large scale. And hopefully over the next few weeks we can demonstrate that with our first on-site trials. Thank you all for your attention.